Hello, everyone. Just a reminder that as I record this on May the 5th, we're right in the middle of traveling through a stream of icy particles in space left behind by the famous Comet Halley. This is the Eta Aquarid meteors on Mars, the Mars rovers. And I'm so honored today to be here with someone who has a long history of working with those rovers. Doug Ellison, hello. It's
Good
so
morning.
good
How
to
are
see
you?
you. Very
Thank you.
well, thank you. So tell me your title at NASA Jet Propulsion Laboratory and just what it is that you do there.
So I am the planning team chief for the Curiosity Mars Rover, which means myself and my deputy team chief Jack, we manage a team of about 20 folks responsible for planning the activities of the Curiosity rover on a day-to-day basis and trying our best to fulfill the requests of our science team. And I also keep my hand in tactical operations as well. So I also operate the engineering cameras on Curiosity as well. And that's a role I also did on the Opportunity rover back in the day as well.
That's so great. So let's look at the view from the Curiosity rover. We're looking at its shadow here and off in the distance at an unexplored part of Mars. So Doug, the average distance between Earth and Mars is about 140 million miles. And I'm assuming you're not set up with steering wheels there at Jet Propulsion Laboratory. So how does your team sitting in a building on the JPL campus in California drive a rover on Mars?
So I'd love a joystick, right? Just point and go. But as you rightly point out, like even when Earth and Mars are at their very closest, it's 5 minutes minimum in terms of the one-way light time, which is as fast as our radio signals go. And actually, fun fact, the little animation you've got running was taken during our last solar conjunction when Earth and Mars were actually on opposite sides of the planet. It's like opposite sides of the solar system. And so then it's more than 20 minutes just one way. So imagine the situation if it was with a joystick, right? You stick it in forward, 20 minutes later, the rover gets that message. 20 minutes later, you then get an image showing you that it's moving. At that point, you've already been driving for 40 minutes and you've gone off a cliff or whatever. So we can't joystick this. What we actually do is we pre-plan 2, sometimes 3, or even 4 days of activities for the rover all at once. And that includes everything. That includes basic engineering housekeeping, right? Taking out the trash and making sure everything's nice and tidy on our flight computer. It's doing what's called remote sensing, which is pointing the cameras around to get high resolution views of our surroundings using the ChemCam laser spectrometer to take pictures and do laser breakdown spectroscopy of the rocks around us. We'll do environmental observations. We'll look for dust devils. We'll look for clouds, that kind of thing. Then we'll get the robotic arm out. And with the robotic arm, we can touch rocks. We can look at them with a microscope. We can brush them clean. We can put a spectrometer on them. And then typically we will stow the robotic arm and then we'll drive. And we'll drive on a good day. A really good drive for Curiosity will be about 50 meters. And that'll take about an hour to an hour and a half. But it's not with a joystick. And what we actually do is plan a drive on a 3D virtual model of the terrain in front of us made from the pictures that we took when we pulled up at our current location. We have this beautiful 3D model of our surroundings in the pictures. We plan the drive, we pick our way between some of the more hazardous rocks, and we'll drive about as far as we can see. So 20, 30, 50 meters on the long end, and we'll basically put waypoints in the ground and ask the rover to make its best progress towards those waypoints. And it's taking pictures as it goes to measure its progress, basically going, well, I was told to get to here. Comparing these pictures, I've now moved a little bit more, a little bit less. I need to go a little bit left, a little bit right, and go from waypoint to waypoint. And sometimes when we have the power, when we have the time in a given plan, we'll also let the rover off the leash a little bit. And we will ask it to, with its own best understanding of the terrain in front of it by taking even more images, analyze the terrain for hazards and keep going to a kind of a more distant waypoint. And we call that auto nav, which is when we kind of let the rover go as far and fast as it possibly can.
So, Curiosity landed on Mars on August 6th of 2012. Let's look at that image, Natalia, that descent image of Curiosity. Yeah. Can you tell us a little bit about the landing and
Yeah, this is
This
one of the
image?
most this is one of the wilder pictures I think we've taken in terms of Mars exploration. So people may remember the Curiosity landing was the first time we used that crazy sky crane landing system with the rocket backpack, lowering the rover onto the ground, onto ropes, and then flying away and destroying itself. But before you got to that scary part was a part that was more familiar with other Mars landings, which is you've got a heat shield, you come in at Mach 25, you've got that kind of surface of the sun temperature at the front, rover's nice and toasty inside at room temperature. You get to about Mach 1.8, Mach 2, and you deploy your giant supersonic parachute. And this image was taken not long after that. So what you've actually got is about a 20-meter wide parachute at the top there. You've got, and you can almost see them. You can see all the risers, the cables that link the edge of the parachute down to the back of what is called the back shell. And the back shell is the bright part at the bottom. The rover is actually tucked up underneath there, with the sky crane kind of bolted to the top of it. And this image is just a few seconds after the heat shield was ejected. And so way further down, and very difficult to find, but way further down in this image is actually the heat shield falling away to the surface as well. And so this is in a somewhat quiescent part of the landing process where we're under the parachute, the radar's getting a look at the ground, we're figuring out exactly where we are, and not too long after this, then that whole crazy sky crane process starts. And this image was taken by the HiRISE camera on the Mars Reconnaissance Orbiter. MRO's been at Mars for nearly 20 years now, taking incredible high-resolution images of the surface, as well as a whole bunch of other really valuable scientific data. And normally, HiRISE points pretty much straight down to take images that are 25 to 30 centimeters per pixel. That's kind of the reasonably good Google Earth, Google Maps kind of style quality imagery. You could count the cars in a parking lot, that kind of resolution. But during our landing, they looked off to one side and took a picture of Curiosity hanging under its parachute, something they managed to pull off with the Phoenix mission. They've done it with us, and they've done it with Mars 2020 as well.
It's amazing. It's amazing to think that that is Mars.
Yeah,
Let's take a look at a
it's wild.
Yeah, it is. Let's take a look at a panorama from Curiosity. So what can you tell us about this? This is a recent one. This is from February of 2025. And I understand that that's not a mountain in the distance. That's the rim of Gale Crater where Curiosity has been exploring.
Yeah, so Gale Crater itself is about 100 miles across. In the middle, there's a giant mountain about the size of Mount Whitney, and we are crawling up the foothills of that mountain. And this is a view from the foothills looking back out towards the northwest rim of Gale Crater itself. That rim of Gale Crater, which looks kind of like a mountain range, right? It looks a bit like driving up the 395 from here in LA up to like Mammoth and looking at Mount Whitney off to one side. It's about 20 miles away.
Kinda,
Yeah,
kinda.
it's extraordinary, and the scale is not dissimilar. It's about 20 miles away. It's about 10 to 15,000 feet tall. But where we've been hanging out most of the time has been kind of the crazy terrain you see in the foreground. It's pretty gnarly, but we're going up the foothills layer by layer, seeing how the chemistry changes, how the geology changes, how the morphology changes. And every time we go up, another few tens of meters, we learn something new about how habitable was Mars, how well did that habitability persist, what can the chemistry and the mineralogy tell us about the environment of Mars billions of years ago when this was still a warmer, wetter place. We found evidence of all sorts of different kind of minerals that tell a story of a far more habitable environment that we're kind of beginning to pick apart the very last vestiges of that habitability as we climb ever upwards into Mount Sharp.
Yeah, I mean, it seems like the whole story on Mars has really changed since the rovers have gotten there to maybe it's this remote possibility that Mars had water in the distant past to Mars had water in the distant past. People have gotten much more certain about it since the rovers have been there.
It's inside joke is that, hey, guess what, we discovered water on Mars again, right? But it's every time we do that, it's more detail, it's more precision, it's more understanding of the context of what that environment was like. But I love that where Curiosity landed, which is actually out on the plains of that gorgeous panorama, before heading up to the foothills, we found some beautiful layered outcrop of rock that, based on the mineralogy, based on the chemistry, based on the morphology, was probably laid down in a kind of a shallow river that was flowing billions of years ago with water so clean you could well have been able to drink it, that was flowing somewhere between ankle and waist deep. That's an extraordinary level of kind of human comprehensible environment that is so incredibly different to what we have now. And Curiosity's job really has been to establish, was that a habitable environment, and what happens to it? And that's what we've been doing ever since, as we climbed through a clay bearing unit that had, there was probably the peak habitability of Mars locked up in kind of those rocks. So this increasingly kind of sulfate bearing unit we're in now, which is more towards the end of kind of Mars as a warmer, wetter place. And we see, as we go from layer to layer, sometimes we see like layering that kind of changes really, really quickly. And it almost feels like we're literally watching kind of Mars die, almost like we're seeing that environment go away layer by layer.
Wow.
You can almost see like maybe these layers were laid down during a slightly warmer and wetter period, and then it was drying out a bit, and then it was a bit warmer. We know which direction it's going, but the clues of what happened are actually locked up in all of these layers.
It's amazing. And so the main purpose of the rovers, the main question that you've been trying to answer is, was there life on Mars? Do we know? We just think, yes, but do we know?
So the Curiosity mission's job has always been, was it a habitable environment? Was it somewhere that life could have lived, and were all the ingredients that it needs there? It's very, very hard to kind of come up with some magical box into which you put in a bit of a Mars rock, and then it says a flag that says yes, there was life, or no, there wasn't. Right? It's very, very difficult. It even gets to what constitutes the definition of life itself. But we know for a fact that it was a very Earth-like environment billions of years ago. We have found so many of the building blocks that life needs, all the way up to things more recently like carbonates, which speak to kind of the demise of that habitable environment, or some results that were published just a few months ago about results we got from the SAM instrument almost a decade ago, but our science team has been figuring out, what do these measurements mean? How do we best replicate them in a lab? How do you best interpret these to find evidence of increasingly long chain organic compounds? And by that I mean like carbon bearing compounds, the sort of ingredients that you need to pull life together. Was it inhabited? We don't know, and it's going to be very exciting to find out. That's for future missions down the way, but it was certainly a habitable environment, and all the ingredients that life needs were definitely there.
And I love the idea that Mars is inhabited now. It's inhabited by our robots, our these extensions of the human mind, and that is just such a cool thing. So just last night I rewatched the great documentary Goodnight Oppie. And I just wanted to mention it because I want everybody who's watching this to watch it. It's really great. And it's about two Mars rovers, Spirit and Opportunity, which they got to Mars in 2008?
2004. Yeah.
2004. So let's play a piece of the trailer.
This is Delta Launch Control.
Go for launch.
3, 2, 1. Engine start and liftoff.
Yeah, it's only a robot, but she becomes a family member.
She becomes a family member. I just love that. It's such a great movie. So it's available on Amazon Prime, and I hope everybody gets to watch it. There were the robots. Those robots were every bit as lovable as the robots in like Wall-E or any of the Star Wars movies. They're very lovable robots.
It's funny. A lot of people say, "Oh, you made your robots look like Wall-E," and I have to point out that folks from various animation studios have visited JPL as seeking inspiration, and indeed, it's the other way around. Wall-E was designed to look like our robots. Our robots weren't designed to look like Wall-E. There's a reason Wall-E has two eyes. Our robots have stereo vision, so they can navigate their way around. But you're right. Goodnight Oppie, we were all, those of us who were fortunate enough to be part of that project, and my role in the Opportunity mission, so at the very end of the MER project, was taking pictures with the engineering cameras on Opportunity. Everyone who was a part of that mission, we feel very, very lucky to have been part of something that was so special, and so special for so long. And then the real kind of the little extra kick in the end was to be a part of something like that documentary that Ryan and his team did such a beautiful job of doing something a little different to most of like the traditional big, beautiful documentaries about big space missions that tend to tell the picture of, you know, how the mission worked and what it found, and that's all good. And that stuff's been done, and it's been done beautifully by many different documentary teams. But what Ryan did was flip the formula on its head and tried to tell our story through the eyes of the rover. And that felt like a real fitting way to kind of close that project out. For a lot of us, I think that documentary represented kind of the closure we needed to finally say goodbye to that mission. And what is really nice is that, you know, when we were all sad about saying goodbye to that robot, when Opportunity finally succumbed to a dust storm, it's weird to think, but we aren't saying goodbye to excuse me, we aren't saying goodbye to 400 pounds of metal, right? That's dumb, that's stupid. What we were saying goodbye to was that cadence of all coming together on a regular basis to figure out what are we going to do with that robot today, how do we make it do it, how do we keep it alive, what can we discover with it. And that teamwork, that camaraderie, that working together on this common goal with awesome challenges, that's what we were saying goodbye to. And I was very fortunate in that I had the Curiosity mission to lean on, and many of the people who I worked with on Opportunity, I now get to work with on the Curiosity mission too. And one thing I think we almost chase this is this feeling of, just like what the MER project was towards the end as well. It's a small team doing the very best we can with what we have to keep the vehicle alive, keep it moving forwards, and keep it making amazing scientific discoveries. It is an extreme privilege to represent the frontier of the human experience, right? That's what this is. And every single day when we try and drive the rover, we get a 360 at the end of it. It's the first time we've ever seen it. No one has ever seen that landscape before, and we're going to keep plowing on into that desolate, magnificent desolation, and keep uncovering new secrets as we keep going together.
And speaking of magnificent desolation, Natalia, let's show the tracks from MRO. So the long, dark, curvy line in the middle of this image is the rover's track, and you can see the rover itself kind of toward the middle of the image, down toward the bottom. It's just a tiny speck. So here's this was taken, I believe, by the Mars Reconnaissance Orbiter in, I think, February.
Yeah.
And here's Curiosity. It's just moving along this landscape, so lonely.
It's a haunting image in some respects. We have been supported by the amazing High-Rise camera and its team on MRO for many years. In fact, they helped find a safe landing site and mapped it, and they mapped all the terrain that we have explored to date and will ever explore with Curiosity. And so they are a partner in our exploration, and they continue to take images of our terrain on an occasional basis, just to monitor it, right? If you have a ground truthing tool in the form of a Curiosity rover, right, you're going to revisit that with all these instruments to see what's changing, and you can compare and contrast between the orbital imagery and the surface truth we get with Curiosity. But what was kind of, I think it was a first with this image, is that, and they take an image maybe every 6 to 12 months or so of where we are. When we're driving the rover, we're only driving normally for an hour and a half, maybe 2 hours every 2 to 3 days. And even when we are driving, because our rover is a little old and it only has a 133 megahertz computer, which is significantly slower than the one in my watch, when we're driving, most of the time we're actually parked crunching numbers with the imagery we've taken to check our own progress as we go. We take pictures, we analyze them, we take more pictures, we analyze them, make sure that we're making the right kind of progress in the right kind of direction, like a incredibly slow optical mouse almost. And so we don't drive that often, an hour or two every couple of days. Even when we're driving, we're only moving about a third of the time. But it just so happened when we saw that high-rise image, we cross-checked it with what the rover was actually doing. For, I think, the first time in our 12-year mission, the rover was actually in motion at the time the image was taken. Now, It's not like you're going to see this cloud of dust as we scream across the Martian desert, right? We were flat out at 0.01 miles an hour. Like we're flat out when we're moving. We're doing 3 or so centimeters per second, right? We're pretty slow, flat out. We do about 100 meters an hour. But the rover was actually moving. It was in progress. My colleague Amy Hale was the one who wrote the commands to do that drive. And so, yeah, she's not going to be busted for speeding by MRO, but the rover was actually moving when that image was taken.
And I think it's so poignant too, because like unlike the human footsteps on the moon that are still there because the moon doesn't have an atmosphere, so they're still sitting up there. Any place the astronauts put their feet, even the tracks of Curiosity will be erased by the wind because Mars does have wind and weather.
We when that image came down and I started looking at it, I tried to track the tracks. I tried to follow the tracks as far back as I could, and frankly, they disappeared to nothing not long after the big image they put out with that press release. They last, depending on what Mars is up to in terms of seasons and wind and the local kind of wind conditions, 6 to 12 months, and then most evidence of those tracks is probably gone. The Opportunity rover actually did the best job of understanding what's happening to rover tracks. Early in its mission, Opportunity drove around the rim of a crater, then went into that crater for about 6 months, then came back out again, and in doing so, crossed its own tracks. And when they did that, they stopped, they turned around, and they got out the microscope and compared the 6-month-old tracks with the brand new tracks. And you could see that, Mars has spent several billion years getting, every little sand grain and every little pebble and rock into just the right place, and it likes it like that. We come along and we drive through it, and it's trying to put it back, right? It reaches a state of equilibrium, like all these, the sand is in the right place, so that with its Opportunity, all the little hematite concretions, and we could tell that the dust was being blown away and the hematite concretions were being kind of re-exposed, and Mars was trying to put things back to how they were before we came along and trashed the place. With Curiosity, it's rare that the tracks are that obvious, but we've been pedal to the metal for the past 9 months or so trying to get to our next cool scientific target. And the terrain just happens to have this right combination of kind of a sandy soil and kind of rocky outcrops that it's leaving behind these quite nice wheel tracks. And in the wavelengths that the HiRISE camera operates, those tracks really stand out. It's absolutely cool to see.
I think I've got some wheel tracks here somewhere. Let me see. Do I still have those? No, I think they took those out. I do want to show a picture of Curiosity itself, though. So there's the rover. It looks very dusty. It's been there since 2012. So what do you think its fate is going to be?
So we will keep trucking along as long as we have the resources to do so. We have a team in our rover engineering team. We have a team literally called the Low Power Future Working Group, trying to figure out how to operate Curiosity with decreasing power. What you'll notice is the gratuitous absence of solar panels on this rover, right? Our power supply is the RTG, the white thing right at the back of the rover, the same kind of power supply that powered the Voyager missions, New Horizons, Galileo, Cassini. What's amazing is it's very, very reliable, right? You don't have to rely on the whims of Mars to clean off your solar panels or avoid dust storms and things like that. But it is a story that goes one way, and eventually we will not have enough power to keep this rover alive. But we're figuring out ways to use the rover more efficiently. We're figuring out ways to stack more activities in parallel on top of one another. And so even over the past few years, we've done things like previously, we wouldn't do anything else while we're talking to the orbiters. One of the awesome things that our science orbiters also do is act as relay satellites. And in fact, the gray cylinder you can see the back corner of the rover is our UHF antenna. We use that to talk to the orbiters. The orbiters send that data home for us. It's much more efficient in terms of kind of unit energy per megabit of data. It's far more efficient to relay that data home. But we've started going, well, what if we took pictures with the engineering cameras during a communications pass? Will that hurt the pass? Will that hurt the cameras? We've tested it. No, it's fine. Now we do it all the time. What if we use some of our science instruments during a pass? And we're testing that right now. What if we drive through a pass? We've begun to test all the various elements of that. We're getting pretty close to unlocking that as well. And so we're trying to find all the efficiencies we possibly can to keep this thing as productive for as long as we possibly can. Ultimately, the RTG will degrade to a point where it doesn't have enough power to keep the thing alive. And at that point, as long as we're scientifically productive, we'll keep on tracking. But there does come a point, many, many years from now, I hope that it won't make sense to try and operate the rover anymore. I hope we get to that point. I hope we get to end this mission on our terms rather than breaking it in some way or something like that. But the rover's getting old, but she's still tracking. She's still got some awesome scientific capabilities, and we'll make the most of them while we can.
That is so great. Doug, I could talk to you all day, but we need to get going. So thank you so much for your time today. Really appreciate it.
Thank you for the invite. It's always a pleasure to talk about what our team gets up to.
Excellent. I've been speaking with Doug Ellison, who is the Curiosity Rover Planning Team Chief. Doug, thank you. Thank you for being here. Fascinating.
Thank you so much.